All right. Hello and welcome everyone to week 7 of interactive live sessions for the course on fundamentals of convective heat transfer. It is being offered by NPTEL and is being taught by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every other week, we will be solving some problems together and having some discussions regarding anything and everything related to the course. So we are already more than halfway past this course. This is week 7 of this 12-week course. So on week 7, we discussed about so before week 7, we have been discussing about fully developed flows through different configurations like a circular duct or through two flat plates, which is a Hagen-Poiseuille flow. So on week 7, we specifically focused our attention on the developing region of the flow in the entrance length and how uh, and we only looked at how assuming hydrodynamically fully developed flow, how the thermal boundary layer develops and how the temperature profile develops for different boundary conditions, like let's say a uniform temperature condition, which is the isothermal case, or the iso heat flux condition, where the heat flux was constant all throughout the walls of the duct. So without further ado, we will jump into today's session and we will have a look at question number 1 of today's session, which is asking us about one very important non-dimensional group which shows up in developing flows known as the Grates number. In fact, the thermal boundary layer development within a uh, hydrodynamically developed flow is known as the Grates problem. So it is named after this researcher called Grates. So what is Grates number defined as? There are four options given below. Option A says G equal to x by d over Reynolds number into Prandtl number. Option B says that the Grates number G is equal to Reynolds number into Prandtl number divided by x over d. And option C says it is Reynolds number into Prandtl number divided by x into d. And option D says it is x into d divided by Reynolds number into Prandtl number. So over here, Reynolds number and Prandtl number are stuff that we already know. X is the axial distance from the entrance of the duct, and d is the characteristic length of the duct. So it could be the diameter of the for a circular duct or the hydraulic diameter for any other case. So have a look at all the options carefully, then you can pick your answer and type in the chat box, or you can unmute your answer as well. Take your time, there's no hurry. So we have question number 1 of today's session asking us, how is Grates number defined? Is it option A, G equal to x by d over Reynolds number into Prandtl number? Is it option B, G equal to Reynolds number into Prandtl number divided by x by d? Is it option C, G equal to Reynolds number into Prandtl number divided by xd? And option D says G equal to xd over Reynolds number into Prandtl number. So we already have one response in favor of option B. Let's see what others have to say. Okay, we have option A. Alright, so let's have a look at the correct solution then. The correct answer is actually option A. Reynolds x by d is the, let's say I have a circular duct like this of diameter d, and x is the axial dimension. So I have y here and x here. So x by d is the non-dimensional axial distance. So x over d is the non-dimensional axial distance, and we divide it by Reynolds number into Prandtl number, which is representative of the the distance of heat transfer. So x over d is the actual distance, and Reynolds number into Prandtl number would be some length scale across which heat transfer has taken place. So this is what g is defined as, and so if g is less than, sorry, so if g is much less than 1, then that means that we are still within the this thing, what is it called, the developing flow. And if it is much higher, then that means that we are past the entrance length and we should consider a fully developed flow. Okay.
Hello, sir.
Yeah.
Yeah, I think answer should be like B, no, sir, REPR divided by X by D.
You sure? Okay,
Before, yeah,
then
it's supposed to be the.
let me check the lecture
Okay.
notes then once, since uh, it was discussed in lecture 1 as far as I can remember. Oh yeah, sorry. Yeah, in fact you're right. Okay, so option A is not the correct answer. It is option B. So it's 1 by Grade's number, which is equal to this thing, and it's 1 by G, which is the non-dimensional axial distance. Yeah, you're right. Sorry about that. So G being much less than 1 would mean that it is a developed flow or a fully developed flow. And G being greater than 1 would mean it's a developing flow. Okay, sorry about this. I had a mistake in my slide. Okay, so we will now move on. We'll move along to question number 2, which is asking us Brinkman number, another number which becomes important in co-wet flows, heat transfer in co-wet flows. So what is Brinkman number defined as? Is it option A, Brinkman number BR equal to mu u square by k delta t? Is it option B, BR equal to k delta t over mu u square? Is it option C, mu u square over Cp into delta T? Or is it option D, Br equal to Cp delta T divided by mu into u square? We have one answer saying that it should be option A. Let's see what others have to say. We have question number 2 of today's session over here, which is asking us, how is Brinkman number defined as? Is it option A, Br equal to mu u square over k delta t? Is it option B, Br equal to k delta t over mu into u square? Or is it option C, Br equal to mu u square by Cp delta t? Or is it option D, Cp into delta t by mu u square? There's no hurry. Have a look at all the options carefully and then try to pick out the correct answer. We already have one response in favor of option A. Let's see what others have to say. Okay, so let's have a look at the solution. The solution is indeed option A. So there is Brinkman number is actually a combination of two other non-dimensional numbers. Can you say which are those? It's actually a product of two more non-dimensional groups. It's actually a product of the Prandtl number and the Eckert number. So Prandtl number is given as mu over alpha, and Eckert number is given as uh, mu u squared by Cp into delta t. Yes, that's correct. I'll check once. It's u square over Cp delta t. This is not there. So mu can be written as mu by rho, and alpha is k by rho Cp, k by rho Cp, and here we already have u square into Cp into delta t. So Cp, Cp cancels out, rho, rho cancels out. All that remains is mu into u square divided by k into delta t, which is option A. That's why option A is correct. Okay. Any questions regarding this one? So this Brinkman number Br is the ratio of the heat produced due to viscous dissipation and the heat produced or the heat transferred due to temperature differences through convection. So in case that Brinkman number is much greater than 1, then that would mean that the viscous dissipation is actually significant. And dissipation has to be considered, which is often ignored when it is not important. So, uh, determining whether dissipation is important or not can actually come from the scaling of this Brinkman number. So, this is how it guides us towards a correct way of problem solving. Okay. So, if there are no more questions, we will keep rolling. We will move on to question number 3, which is an easy one. It's asking us for uniform wall temperature condition, the value of Nusselt number for hydrodynamically developed and thermally developing flow in a circular duct is what? Is it option A 3.614, option B 3.66, option C 4.021, or is it option D 4.36? We already have a quick response saying it's 3.66, that is option B. Let's see what others have to say. Okay, so we are discussing question number 3 of week 7 now. Uh, the question is that for uniform wall temperature condition, the value of Nusselt number for hydrodynamically developed and thermally developing flow in a circular duct is what? Is it option A 3.614? Is it option B 3.66, which already has two responses in its favor? Is it option C 4.021, or is it option D 4.36? Alright, so let's have a look at the solution now. The solution is indeed option B 3.66. So it turns out it's the same value for for thermally fully developed flow as well. So what happens is, in a long enough duct, the effect of the entrance region would soon die out, and it's the developed region which actually dominates the behavior of the thermal behavior of the system. So for thermally developing flow, the value of Nusselt number is equal to that of a fully developed flow as well, given that L is sufficient, the length of the duct. Okay. Any questions regarding this? All right. Okay. So we will keep moving on. We will move on to question number 4 now, which is asking us to consider the following statements about Brinkman number. There are two statements given below. Statement 1 says if Br much greater than 0, the temperature rise due to dissipation is significant. And option 2 says that the Brinkman number is important in case where a large velocity change occurs over short distances. Then, so Some of these statements might be correct, might not be correct. You have to pick out the correct combination from the options given below. So option A says that only statement 1 is correct and not statement 2. Option B says only statement 2 is correct and not statement 1. Option C says both of these statements are correct, and option D says none of them are correct. So all possible combinations are there. So read the statements carefully first and then try to pick out the correct answer. So we have two responses in favor of option C. Okay, so let's have a look at the solution. And both of you are correct. So it is indeed option C that both 1 and 2 are correct. So this is something that we briefly discussed earlier, that if Brinkman number is much greater than 0, then that means that the dissipation coefficient is actually significant, the viscous dissipation. So temperature rise due to that we have to consider. And the second statement says that the Brinkman number is important in a case where large velocity change occurs over short distances. So why is that? Because if you look at this dissipation coefficient, this is equal to mu into, let's say, some dou u dou y whole square. So if this temperature gradient is large, which occurs in a case where there is a huge velocity change over a very short distance. So this may be delta u, and this is, let's say, x. So if x is small and delta u is large, this type of a case would result in a high dou u dou y square, and that would in turn result in a high viscous dissipation, and that's where Brinkman number becomes important. So one of the examples where this kind of a situation might occur is in a uh, lubrication system. So let's say there's a journal bearing like this. This is fixed and this thing is rotating. It's a shaft uh, within a journal, and there is a liquid lubricant in between the shaft and the bearing. So in this case, there is a very high U over here. So industrial shafts and let's say shafts in uh, engines, both in automobiles as well as for Air Force applications. In all cases, aerospace applications, the shaft velocity is actually quite high. So this U would be quite high, and the bearing itself would be at rest. So there will be this huge uh, change in velocity within a very narrow gap. So I drew this in an exaggerated fashion, but in a real journal bearing, this distance, this is actually very small. It's just a thin film of lubricant around the shaft. So there, this delta x is very small and u is very large. So in an application like this, the viscous dissipation as well as Brinkman number becomes important. So this would lead to some design challenges, like you have to take the heat out of that system, otherwise the temperature might rise to uh, non-operational number. So if it becomes too hot, then it might cause some problems. So that's why the thermal design has to take care that there will be sufficient heat dissipation out of the system so that the temperature doesn't rise too much. Okay. Any questions? All right. So if there are no questions, we will keep moving. We will move on to question number 5 of today's session. Here also three statements are given, and some of them are correct, some of them are not. You have to pick out the correct combination from the options given below. So read the statements carefully first. Statement 1 says that shape of the fully developed temperature profile is the same as the temperature profile of thermally developing flow. Statement 2 says that for similar conditions, the values of convection heat transfer coefficient are more in forced convection than in free convection. Statement 3 says that in thermally and hydrodynamically fully developed flow of a fluid with constant temperature profile in a circular duct, the wall heat flux increases exponentially with x. So here what I mean by constant temperature profile is that the wall temperature is constant, T wall. So among these three statements, there are four options given below. So option A is only 2 is correct. Option B is both 1 and 2 are correct. Option C is both 1 and 3 are correct. And option D is 1, 2, 3 are correct. So we have one answer in favor of option B. Let's see what others have to say. There's another response in favor of option D, 1, 2, 3 are correct. Okay, so let's have a look at the solution then. The solution is option A, that is only 2 is correct. So for similar conditions, the values of convection heat transfer coefficient are more in forced convection than in free convection. This comes from intuition, right? So for a free convection, there will be a natural current set up by the density differences and all. But in forced convection, you can use a much higher velocity to enhance the heat transfer. So statement 1, shape of the fully developed temperature profile is something like this, right? And the shape of a developing profile, let's say this is how my thermal boundary layer develops. So in this case, there will be a flat part over here where the thermal development hasn't reached yet, and within the boundary layer it would be the same as the thermally developing flow. So the shapes won't be exactly same. There will be a flat part in between for a developing flow, and so that's why this one is incorrect. And statement 3 says in the thermally and hydrodynamically fully developed flow of a fluid with constant temperature, not profile, of constant temperature in a circular duct, the wall heat flux increases exponentially with x. So we know that first of all it does not increase, let alone exponentially or in any other fashion. The wall heat flux actually decreases. So that's why statement 3 is also incorrect. So from all these, it's only option 2 that is statement 2 that is correct. So that's why statement A saying that only 2 is correct would be the right answer. Okay. Any questions regarding this? Okay. So then we will keep moving on. We will move on to question number 6 of today's session, which is asking us that match the following for co-ed flow with viscous dissipation. So for co-ed flow with viscous dissipation, we had derived the expressions for Nusselt number for both the top wall as well as the bottom wall. Now mind you, the top wall is the one that is moving with a velocity u, and the bottom wall is stationary. So it's something like this. This is at a temperature TH, let's say, or I'll call this T top, and I'll call this one as what happened? Wait a second. The slides are visible, right? Okay. First of all, I'll call this T top and this one as T bottom. We have one answer in favor of option B. See what others have to say. So there are these two expressions for Nusselt number at the bottom wall and Nusselt number at the top wall. You have to match them with the correct expressions. There is 1 and 2. One says 2 minus Brinkman number. This can be written as 2 minus BR. And option 2 says it's minus 2 into uh, 2 plus Brinkman number BR. So you have to match the following, and there are only two options possible. So it is either A1 B2 or it's A2 B1. Okay. Okay, so we have two responses in favor of option B saying it's A2 B1. Okay. Yeah. So let's have a look at the solution. The solution is option B, that is A2 B1, where A is this and B is this. So the Nusselt number at the bottom would be minus 2 into, uh, sorry, would be minus 2 plus Brinkman number. Is it hanging again and again? And the Nusselt number at the top would be 2 minus Brinkman number. So that's why option B is the correct one. Okay. Any questions regarding this? If not, we will move on. Sorry. So we'll move on to question number 7 of today's session, which is asking us that for a hydrodynamically fully developed and a hydrodynamically developed, sorry, so this would be hydrodynamically fully developed and thermally developing flow through a circular duct with constant wall temperature. What is the value of Nusselt number at x equal to 0? Is it option A 0? Is it option B 3.66? Is it option C 4.36? Or is it option D infinity? So for a hydrodynamically fully developed and thermally developing flow through a circular duct with constant wall temperature, what is the value of Nusselt number, the local Nusselt number at x equal to 0? Is it option A 0, option B 3.66, option C 4.36, or is it option D infinity? Okay, we have one response in favor of option A saying it's 0. Okay, now the responses. So let's have a look at the solution. Solution is actually d infinity. So if you look at the graph of Nusselt number versus x, so this is local Nusselt number nux. This is actually reaches uh, asymptotically reaches a constant value as x tends to infinity, but as uh, x tends to 0, it actually increases like this. And sorry, this last part won't be like this. So this would go something like this. So as x tends to 0, the Nusselt number actually tends to infinity. Because let's have a look at the let's have a look at what is going on here. So at exactly x equal to 0, there the boundary layer just starts to grow. So the thickness of the boundary layer delta is actually delta tends to 0 over there. So you can imagine that the uh, temperature gradient there, dou T, dou Y, which scales as delta T, that is the distance between or the temperature difference between the bulk mean temperature over there and the T wall. I'm calling this as delta T. This difference is over a very small distance, that is delta. So this would result in a very high amount of heat flux over here at x equal to 0. So that's why Nusselt number, which is sort of, so that's why H would be high. So the the heat flux being high would mean that the convective heat transfer coefficient will also be high, finally meaning that the Nusselt number will also be high. So that's why as x tends to 0, Nusselt number tends to infinity. And as we have a finite value of x, this Nusselt number also comes and achieves a finite value. And ultimately, uh, after x reaches a significant finite value, this Nusselt number would go down and asymptotically try to reach some constant value depending on the boundary condition. So for let's say this case where we have constant wall temperature, it would finally tend towards 3.66. But at exactly x equal to 0, this Nusselt number would actually be infinity. Am I making sense? Any questions regarding this? Okay, so if there are no questions, we will move on to today's last question. That is question number 8, which is asking us that for a fully developed flow through a circular duct, what is the non-dimensional velocity profile U star? Given that U star is defined as the ratio of U over U mean, that is the mean velocity of flow, and eta is the non-dimensional radial coordinate given as r over r0, where r0 is the radius of the circular duct. So imagine this is the circular duct, this is r0, this is r, and u star is given as some u, which is a function of r divided by u mean, which is a constant number for that actual location. So, and if it's a fully developed flow, then constant. Uh, it's a constant number. It does not depend on any variables. So, what would be the non-dimensional velocity profile look like? Is it option A, u star equal to um into 1 minus eta squared? Is it option B, u star equal to 2 into 1 minus eta squared? Is it option C, u star equal to 3 by 2 into 1 minus eta squared? Or is it option D, u star equal to 2/3 of multiplied by 1 minus eta squared? We have one response in favor of option D. Let's see what others have to say. Remember, this is for a circular duct. We have one response in favor of option D. Let's see what others have to say. We have another response in favor of option B. Alright, so let's have a look at the solution. Solution is actually option B. So what happens is for a circular duct, solving again quasi equation, we know that the velocity u as a function of r is given as uh, the u maximum multiplied by 1 minus r squared over r naught squared. So now if I okay, another thing that we know is that this u max is twice the mean velocity um. And now if I non-dimensionalize this, so I'll have u equal to 2 into 1 minus eta squared. Okay, wait a second. All of these options are wrong. Won't be present in any of the options given here. So it will be just 1 minus eta squared, 2 into 1 minus eta squared, 3 by 2 into 1 minus eta squared, and 2 by 3 into 1 minus eta squared. Yeah. So now if I take this under there, so it will be u over into 2 into 1 minus eta squared. And this is nothing but this u star. So u star would be equal to 2 into 1 minus eta squared. So it's option B that is correct. And sorry about that. There shouldn't be in the right hand sides of these options. Does that make sense? Is everything clear?
Yes.
Okay, so that brings us to the end of today's session. Thank you all for joining and participating. We will meet again same time next week.
Thank you, sir.
Okay, thank you.
Thank you.